What do we mean by analog input? Analog values are continuous values, such as temperatures and pressures. While we tend to think of them in digital terms, at some point we have to convert them from the continuous world into our digital world, and this is where analog inputs come in. Voltage signals in the range of plus or minus 20 volts or so, and current signals in milliamps are commonly used as both analog inputs to PLCs. Every PLC manufacturer has I/O modules to deal with these kinds of signals, along with other, more specialized modules. The simplest of these types is the voltage input, so we'll tackle it first. Here, we have a simple circuit that converts the position of a knob into a 0 to 5 volt signal and connected to a generic PLC voltage analog input. When the knob is on 0, the input to the PLC will be 0 volts, and at the other end of the knob's rotation, the PLC will see 5 volts. What the PLC sees as the result of the conversion of the voltage to a number depends on the PLC and its configuration. For instance, some of the older Allen Bradley PLC models would return an integer ranging from 0 to 8191 for an input of 0 to 5 volts. Usually, the newer models of PLC will allow more flexibility in how the value is returned, so that you can scale the numeric value to whatever your application needs. The PLC program can use this input to control, for example, the brightness of a light bulb, the output of a heat source, the speed of a motor, or how fast a counter counts. While the voltage input is capable of almost everything we need in general applications, because of electrical noise interference from other devices, current mode signal transmission is a better choice for signals that need to travel over any real distance. For this reason, many applications use current inputs. From the PLC end, a current mode interface is generally a voltage mode interface with an added high-precision resistor. While the resistor is often inside the PLC module and switched in by a jumper or connection position, it is effectively the same. This is an example of a device-powered current source. The field device is getting its power from another source. The current signal is sourced from the positive terminal on the measuring device, traveling to the positive terminal of the PLC. Since there's a limit to how much voltage is available in the loop, we will usually limit the overall resistance on the measuring end of the loop to 500 ohms. Often this is called out as part of the field device installation instructions. Another common type of analog device uses the 4 to 20 milliamp signal as its power source, reducing the required complexity on the field end. Here's an example of a loop-powered arrangement. The main addition to the circuit is the separate power supply on the PLC end. Note that the positive and negative measuring device connections are different from the previous example. The current comes from the power supply in the positive terminal of the loop-powered device, and out the negative terminal and into the positive PLC terminal. What we have covered so far have been generalized inputs, used where the field signal is set up as a conditioned input for the PLC. The next types of inputs we will cover are specific to two different types of common temperature measurement devices that are common enough to be worth building specific modules for. There are thermocouples and resistance temperature detectors, or RTDs. The older type of temperature device is a thermocouple. This type of device generates a small signal in the millivolt range, depending on the temperature at the junction, the point where two different metals touch to create the voltage. A thermocouple measurement module is designed to process these tiny signals into temperature readings, and they have several somewhat picky features. The wires used to connect the thermocouple to the module must be made specifically for that type of thermocouple. The wrong kind of wire will make the signal useless. Because the signals are at such a low voltage, the wires need to be well shielded and carefully routed away from higher voltage wiring. Finally, these sensors need cold junction compensation, a feature which is built into most thermocouple modules, but some require external devices for this purpose. The temperature range of a thermocouple is specified by a single letter, i.e., a type J thermocouple is a common variety with well-known characteristics. RTD, or resistance temperature detector inputs. The newer RTD, or resistance temperature detector, is generally more robust and accurate than the thermocouple, but the older sensors are still quite common because they are both designed into older equipment and capable of operating at temperature ranges that RTDs are not made to handle, including up to white heat, 1600 degrees Celsius, in unique applications. As the name implies, the resistance of the device changes with its temperature, so measuring the output is relatively straightforward. They generally come in 3 and 4 wire configurations and several temperature ranges. This video has been a basic introduction to the most common sorts of analog inputs used in PLC-based applications. Each of the types covered here has its quirks, and the ways the PLC inputs are built differ between manufacturers and PLC models, so we have just covered general principles without enough detail to implement them in any given PLC system. We have also not attempted to cover every type of device. Each manufacturer has unique ways of handling measurements, and there are many other sorts of sensors that we have not included here.